Hello, this is the first part of the chapter 3.3, and we will talk about the Cramer's rule, which is really cool. So let's start with a very interesting procedure. If we have a matrix and a vector, we can substitute one of the column of the matrix with our vector B. And of course, matrix and vector should be appropriate dimensions. So this probably sounds like a weird definition. Let me give you an example. Let's have a really simple matrix A. First column is 1, second 2s, and third is 3s, and the vector B over here. So in this case, let's just apply our definition and let's calculate all the AIs of B. And because I is a column number and our matrix A has a 3-column, we will have 3 total of this, this kind of like replacement matrices. Let's start with A1. So our index of the vector I is 1, which means that we take the first column and we substitute the vector B there as it is. Okay, so let's try to see what's happened when we try to construct A2 of B. Again, our index is 2 here, so we take second column and substitute vector B. Finally, let's see what's happened with matrix A3 of B. So now our index is equal 3, so we take third column and substitute vector B there. And that's it. That's so simple. And you're probably wondering, why do we need such a strange procedure? Why do I want to substitute random vectors inside the matrix? The reason for it is that that's kind of substitution gives us a pretty cool way to solve a linear equation. So if we have a matrix equation, AX is equal B, we can find our vector X by basically every component of our vector X can be found by dividing the determinant of this substitution matrix AI of B by the determinant of the full matrix. And that's called a Cramer's rule. And although it's a kind of a weird way to solve equations, it's probably much easier to solve it by reducing to the echelon form. But it's so cool that I think everybody should try to use Cramer rules at least once in their life. Let's just try to use it. Let's try to apply it to this reasonable system, a reasonably simple system of linear equations. Okay, let's write it in the matrix form first. And again, we're just subtracting the terms in front of x1 and x2, and we write them as a matrix. From the first column, we get 3 and minus 5 multipliers for x1. From the second column, we get minus 2 and 4 multipliers for x2. And of course, our vector B is just the right-hand side, 6 and 8. Okay, so let's try to make this substitution matrices, AI of B. Okay, let's try from the first. We only have 2 columns here, so that's only 2 matrices. So our first matrix, A1 of B, we take the first column because our index is equal 1 and put our vector B there, 6, 8. And our second column is exactly as an original matrix. Okay, looks straightforward, I hope. Let's try with A2 of B. And again, we just, since our index is 2, we'll leave the first column of matrix A as the same as it is and put our vector B as a second column. Okay, so now we can use a Cramer rule to actually calculate x1 and x2 by just calculating determinant of 3 separate matrices. Let's try with x1. So again, our index of x is 1, so we put the determinant of the same index for our substitution matrix A1 of B and divide it by determinant of a full matrix A. And since we already find our matrix A1 of B, we just put it in the numerator. The determinant of our full matrix A going to the denominator, and all we have to do is just calculate 2 by 2 determinants, which give us a x1 equal 20. And then we repeat it for the second component of our solution, vector x2, because our index is 2, we are taking the determinant of matrix A2 of B and divided by determinant of A. And again, just two simple determinants of 2 by 2 matrices. Here, when we calculate an answer, we get x2 is equal to 27. And that's our solution. If you don't believe me, you can go ahead, reduce this matrix A to the echelon form, and confirm this solution. And I hope you will enjoy the process as much as I do. So go ahead to the end of the chapter 3.2 and calculate several systems of differential equations using the Cranber's rule. I promise you will like it.